Hi everyone, welcome to Chemical Bonding Basics. Now, if you've been reading the book, you'll know that I've changed the order of the chapters around a little bit. I like to kind of completely finish atoms before moving on to Lewis structures, and the reason for that will become evident when we talk about expanded octets, because if you understand an orbital box diagram, it's plain sailing. If you haven't met orbital box diagrams before expanded octets, it makes no sense. So we'll use that orbital box theory to explain some interesting things with Lewis structures, but that's later in the packet. Okay, so for now, let's talk about the basics. All right, so we've already met Lewis symbols, which are just the outside electrons as dots, right, for different atoms. And of course the column number is the same as the number of dots, right? Okay. And then we saw the kind of the more detailed, all the dots, you know, the complete dot diagram for atoms. Okay, so we've seen the old school dot diagrams. And if you remember the old battleship analogy, carbon is column 4, row 2. So it's in the second layer, row 2. Column 4 on the outside. So using just the position, any of the first 20 elements up to calcium, you can do the battleship. You can find from their position, you can find their dot diagram. Okay, so let's just try that, just a bit of a quick review. So let's do a dot diagram for lithium and fluorine. Okay, so grab the periodic table. Everyone has a periodic table, right? Okay, so there's lithium, element number 3. So I'm going to do 3 electrons. I'll do the alphabet. I'll just build up layers. But if you want to do battleship, it's column 1, one on the outside. Row 2. Okay, so lithium, real quick, 3 electrons, 1, 2, 3. Fair enough, right? Fair enough. If I did the Lewis for that, it's just a single dot, isn't it? Okay. Now, fluorine, element number 9. All right, element number 9, so it's row 2, column 7, all right, row 2, column 7. So fluorine, 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. Row 2, 2 layers, 7 on the outside, column 7. Fluorine, of course, just the outside electrons for Lewis. Oh. There we go. Fantastic. So hopefully that's a nice review for you. Okay, now I already kind of what's the phrase, let the chicken out of the bag? I don't know, I let something out of some bag, right? So I already told you the secret, right? So turns out, and this is kind of reinforced by our last packet when we looked at kind of how full octets, what do they do? Well, if you actually worked out, so say you try to add an electron to an atom with a full octet, right, to make it a minus ion, nothing would happen because the effective nuclear charge is essentially 0, okay? All right, and if you then try and take one away, the effective nuclear charge, because it's got like a full outer layer and then just a couple of electrons maybe screening, okay, the effective nuclear charge is high. So for full octets, full outer layers, try and remove an electron, effective nuclear charge is super strong, it kind of keeps it there. If I try and add an electron, the effective nuclear charge is essentially 0. So this really explains why atoms with full octets are stable. Okay, so every atom in nature tries to get to that position, and we saw details in the last packet about why full octets are stable, but I like to say, full valence layer, because that helps with hydrogen and helium. But anyway, atoms like to be having a full outer layer, a full valence layer, because it's the most stable electron configuration. So that's why the noble gases are stable. They don't react with anything, okay? They are happy as they are, okay? But everything else, if you think about it, it's Lewis structure or it's dot diagram, whichever one you choose, there'll be gaps in that outer layer, okay? So it will either give away electrons, take electrons, or share electrons to get that full layer. So everything, this is a key fact, everything when bonded has a full outer layer, okay? And we'll see that concept again in a moment. But every time you write a Lewis structure, that has to be true, okay? So that's the trick, all right? Now, here's a couple we saw before. All right, here's a couple we saw before. So I'll just do them quickly, right, because we've done them before. If I do an ionic bond, right, so if I do lithium, fluoride, so there's lithium, we just did it on the previous page, right? There's a lithium atom, and I'm going to bump it into a fluorine, all right? So let's do crosses for fluorine, because when we have 2 atoms, it's conventional to do dots and crosses. Okay. If you think about it, fluorine has 7 on the outside, so it has space for 1. Fluorine has an effective nuclear charge of 7, right? It's in column 7. Lithium has an effective nuclear charge of +1. So in the battle, this one's 7 times stronger, isn't it, right? So when they bump together, that electron goes over. So it's attracted just based on the difference in effective nuclear charge. Pee Wee Herman versus Arnold Schwarzenegger, right? Okay. And then what do we get? Well, we get lithium with just 2 left. Now it's a +1 ion now, so I'm going to write that. Okay, there we go. And it looks like, why did it only lose 1? It's the weakest, one of the weakest elements, right? Why did it only lose 1? Because now it's got a full layer underneath. Those electrons are now super tightly held, if you think about it, right? So that looks like helium. It's stable. It's isoelectronic with helium. Fluorine, one, 2, 3, 4, 5, 6, 7, 8, 9. There's its 9 electrons, 7 on the outside. There's the extra 1. It's got a full outer layer now. It's stable. It looks like neon. All right. Okay, so ionic bonding, big difference in electronegativity. But both partners at the end of the day are stable because they have complete outer layers. They look like noble gases. The key word, if you remember that key word, is isoelectronic. Cool word. Okay. Try and slip the word isoelectronic into a sentence today. That's your mission. That's your secret mission. All right. Okay. Or is that just me that does that? Okay, it's all right. Next one then. So F2, 2 fluorine atoms, it's a molecular element. So the electronegativity is the same. So they're going to share electrons because they're both pulling with equal strength. The tug of war is a draw or tie, right? Okay. So you know, we can twist and turn atoms in space, so we can have it kind of facing in a different direction. So I'll do it kind of looking the other way, so to speak. So there's my first fluorine, right? And you know, we've done this before, so you've seen this before. Here's my second fluorine. Did this conventionally. Now, if you remember what we did last time, and there's that gap, I said, hey, in your mind, just put these things together and see what happens. Well, that electron's going to go in there, that one's going to go in there. What do we get? Turns into fluorine, 2 on the inside, and then this outer layer, which overlaps with that one's outer layer. Okay? 1, 2, 3, 4, 5, 6, 7. And then here, 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. So by sharing, we have complete outer layer. So if I just think about that overlap as being a shared region of space, both owning it, this atom has 8 on the outside, this atom has 8 on the outside, acquired by sharing. They're both isoelectronic with neon. Okay. Now, chemistry at its heart is a very, very simple thing because atoms bump into each other and they stick. Why do they stick? Because they somehow acquire, when they bump, either an electron jumps over and you make an ionic bond, plus attracts minus, or they share electrons and you make a covalent bond. So atoms stick in one or two ways, ionically or covalently, but the underlying mechanics is the same. Each atom before did not have a full layer, and afterward it did, and it acquired that full layer by either theft or sharing. Okay. Now, this kind of reminds me of course, soccer, aka football, right? So I grew up in the 1980s in England, and at the time, we had a once-in-a-generation player named Paul Gascoigne, right? Now, there he is, right? So that's Gaza, right? Because all the star players, you know, have the one name, like Pele, Maradona, stuff like that, right? So there's Gaza, right? Paul Gascoigne, okay? And he was awesome. He was the captain of the Tottenham team. He was captain of England team. Once-in-a-generation player, really, really good player, okay? Unfortunately, Paul Gascoigne had a bit of a kind of a darker side, and he had kind of a thing where he had like this kind of fast lifestyle where he'd go out to nightclubs and you'd see him in the tabloids all the time. And this is a very, very famous picture from the 1980s. Now, in the 1980s, we did not have cell phones, right? That took pictures anyway, right? We had actual cameras with film in. And this picture is famous because it was taken outside Stringfellow's nightclub in London. And here we have a gyro, right? Okay, it's 4 o'clock in the morning. That's Paul Gascoigne with a gyro, drunk, outside a nightclub in West London. And the next day is an England game where he played really poorly, right? So that picture was actually sold to the Sun newspaper for, I think, £100,000 or something. Someone literally was outside the nightclub. They ran into a drugstore and they got one of those cardboard disposable cameras, snapped that, so they spent $5 and made $100,000. Okay. And it's kind of a sad story. I mean, if I can find a suitable picture on the internet, I'll throw it up, right? But in his later years, Paul Gascoigne, it's a bit of a sad story because he just, you know, he kept up his kind of ways, overeating, over drinking, and he got, of course, larger and he got slower and he dropped out of the England team. He got larger and he got slower and he dropped out of the Tottenham team. And it's a bit like, you know, when someone's not quite as good as they were, what do you do with them? Well, they go to the minor leagues, right? So, you know, if you're a baseball fan, you know, you're a Cubs fan, where do they send their players? You know, they send them to Iowa, right? If you're an NFL fan, where do they send them? Probably to NFL Europe or Canada or something, right? If you're an English Premier League team, where do you send your has-beens, right? You actually send them to Scotland, okay? And here's a picture of Paul Gascoigne playing out his career with Glasgow Rangers, right? And my favorite expression describes both chemistry and Scottish soccer. Chemistry is a bit like Scottish soccer. It's just a bunch of round things bumping into each other. Okay, so if you remember that, you can remember chemistry. All right, so now, what we're going to do, we're going to make these Lewis structures. Very simply, a Lewis structure is a map of where valence electrons are in molecules, okay? And you construct a Lewis structure by combining Lewis symbols. So think about those Lewis symbols we've seen before as Legos, and we combine them to make Lewis structures. Now, we don't have to do this whole big, elaborate, you know, pushing them together and drawing the whole deal, right? There are some certain rules that make it quicker, okay? But before we can apply those rules, we got to kind of think in some more detail about the Legos we're going to stick together, all right? So here's the key fact though. So the number of bonds, and we'll see that as a stick, right? So you've seen these kind of lines, these little sticks in the Lewis structures already, baby, okay? The number of bonds an atom forms, it's valency. So valency is a chemistry word, it's an important word. It means bonding, right? So valent electrons are bonding electrons. Valency is number of bonds made. Okay, so maybe write that there. Okay, so the number of bonds an atom makes, its valency, is the same as, and I think we've seen this concept before, the number of unpaired electrons in its valence layer, because those unpaired electrons in the valence layer will go out and find partners on neighboring atoms, and we already saw that, right? So let's go back at that first example we saw. So that was an unpaired electron, and it went and find a partner, right, from a neighboring atom, okay? So single, single come together to make a pair, okay? So that's how covalent bonds are formed, and just so we're clear, covalent bonding is where we're going, okay? We use Lewis structures to describe covalent bonds, shared pairs, okay? Now, let's make our kind of cheat sheet, right? So what we're going to do is look at some important atoms we use to make organic materials. So, you know, organic chemists use this all the time, okay? And this is kind of our playlist. There's more than 100 atoms in the periodic table, but we only use probably 10 in kind of everyday life in organic chemistry, right? So it's the chemistry of carbon and the surrounding atoms, essentially, okay? So we'll do the atom, number of valence electrons it has, which will be the same as the group number, all right? And then we'll say, hey, because we know it's group number, let's just, you know, points of a compass, make the Lewis symbol, and then just interrogate that Lewis symbol and say, well, how many of those outer electrons are by themselves, singles? That's the number of bonds then it will go away and make when they pair up, right? So carbon can peak, you know, have a periodic table ready to go. So carbon, of course, column 4, nitrogen column 5, oxygen column 6, hydrogen over there, column 1, chlorine and fluorine column 7. Okay, so I have that on the side and we'll just fill it in. So carbon, number of valence electrons, obviously 4, right? Okay, it's Lewis there. Now, let me pause. For effect, I'll do this. How many bonds is carbon going to make? It's going to make 4 bonds because it's got 4 unpaired electrons. We say carbon has a valency of 4. Interesting. Okay, next one, nitrogen. Nitrogen is the next column over, column 5. So it's going to have 5 valence electrons. Now we see something very interesting here, right? Remember, nitrogen was our first of our 30-something New Yorkers, right? So 1, 2, 3, 4, 5. Now this is important because we've seen the first case of we've gone around the points of the compass and we start to go around again. So 4 points, carbon has 4 singles. 5 electrons, well, I've got to go north again, okay? So that renders that pair inert, right? Because it's not looking for a partner anymore, right? Okay, so how many bonds does nitrogen make? Nitrogen only makes 3 bonds. In fact, if I kind of just jump ahead real quick, this will make sense on the next page, but carbon will always have 4 sticks because it makes 4 bonds. Nitrogen in any Lewis will only have 3 sticks, and that lone pair is still there. We call it a lone pair. Okay, so a pair of unreactive electrons which are filled, going around the points of the compass for the atom, are called a lone pair. Okay, oxygen. Column 6, right? 6 valence. 1, 2, 3, 4, 5, 6. How many bonds does oxygen make? You should probably remember this because we've kind of drawn this structure already with oxygen. It's going to have 2 bonds, right? Oxygen always has 2 sticks. If you remember water, H2O, there'd be an H on the end of both of those sticks, right? So oxygen, 2 unpaired electrons makes 2 bonds. It has a valency of 2. So we say, hey, 2 unpaired electrons, valency of 2. Now be careful, right? Because oxygen has 6 valence electrons, but it doesn't make 6 bonds. It makes only 2 bonds. So 6 valence electrons, valency of 2. All right. See if we can do the last 2. Chlorine and hydrogen. All right. Okay, here we go. Chlorine, column 7. 7 on the outside. 1, 2, 3, 4, 5, 6, 7. Interesting. Now, I love chlorine because it reminds me of Kim Kardashian, right? It's got lots of bling, but it does very little work, okay? It's got 7 valence electrons. How many of those are working? 1. Okay, so whenever we see chlorine, it's just got the 1 bond, right? Okay. Hydrogen. Hydrogen's only in row 1, right? So it doesn't need 8 on the outside, so its Lewis is going to be a little bit different. It's got 1 unpaired electron, right? Column 1, 1 unpaired, and we can do that. Okay, it makes the 1 bond. Hydrogen essentially is decorative, right? You can basically surround any atom with hydrogen and it will make bonds, right? Because, there we go, single bonds. All right. So hydrogen will always look like that. Okay, so there's your cheat sheet, right? But we're not done with the cheat sheet. I can make it even more useful, all right? Okay. Now then, this you will not find in the book, but it allows me to answer virtually any organic chemistry question about Lewis structures like it's nothing. Okay, now here's the thing, and you can try this, right? And if I can find a picture, I'll put it up, right? Go on the internet and look for like any kind of organic chemistry professor, right? So organic chemistry professor, UIC, whatever you want, right? And eventually you're sure to find a picture of someone with a giant molecule, posing with a giant molecule, right? A giant molecular model, right? And you're kind of like, wow, that is so cool. Look at that model they made, right? If you ever watched The Big Bang Theory, there's a kind of a DNA helix always in the background of a big old molecular model, right? Okay, now, I think, wow, that's really impressive. How did they put that molecular model together? Well, it's not hard at all, right? If you just understand the rules of valency, how the atoms stick together, making those big molecules is easy, making the small ones is really easy, right? And I'll show you the kind of the easy method to make simple Lewis structures in a moment, right? Okay, but here's my analogy, right? Okay, now let's think of water for a second, right? Okay, if I did, and it's right here, actually, let's just do it right here. So here's my regular Lewis, right? So 1, 2, 3, 4, 5, 6. That was on the previous page, right? Now, up here. Here's Julie Andrews, right?
The hills are alive with the sound of music.
Sound of Music, awesome movie, right? Okay. Now, Julie Andrews actually reminds me of Oxygen. See, she has these two arms here, okay? It turns out that if you think about it, each unpaired electron is kind of like a hand that needs to be held. Here we go, right? So oxygen, this is, now never write this on the test. It's called the easy Lewis symbol. This is just between us, right? Okay, so instead of writing these single dots as single dots, I know they're going to go off and form bonds, right? So it's almost like they're going to shake hands and make a bond, right? So I'm going to draw each dot as, if you like, half a stick, right? And half a stick from another atom, and they hold hands. That's what I call an easy Lewis. And all we're going to do is have the atoms hold hands, right? That's the easy way to do it. What's the valency? Well, it's going to have two unpaired. It's going to make two bonds, right? So think about it. Now, if I go up here, I can kind of show you, right? So here's Julie Andrews. I'm drawing her like an easy Lewis, right? There she is, right? Okay. Now, what was Julie Andrews' job in the movie? Do you remember? She was a governess. She was a nanny, right? So if I do my, there's the nanny, right? Here's the small Austrian child, right? So here's hydrogen, which just has the one electron, right? So it just has the one hand that needs to be held. All you do to make a molecule, and this is why it's so easy, you put the one with the most sticks down first, and then you just surround it with the other atoms to be bonded, okay? And you draw their EZs, right? Okay? And then you just have them hold hands. So each half stick turns into a whole stick. Ah, that's how you do it. Now, if I drew all the dots, I would get this, right? So if I look at the valence layer, hydrogen has 2 in its valence layer, 2 in its valence layer. That's what it wants, full layer. Oxygen has 8. So by following the rules of valency, making sure each atom has the right number of sticks, which is the same as the number of unpaired electrons, it's always going to work. Okay, now if you can kind of use my method, that is awesome. You can very easily cobble together atoms to make molecules just by plopping them on the page, writing their EZs and having them hold hands. You can do the more formal way to do it, and in the book and other teachers do that, right? But I'm showing you the trick. All right, so carbon, let's get our easy Lewis, right? And then we just have them hold hands. So carbon, well, you know, has 4 on the outside. If ever asked, the Lewis symbol for carbon, that's what you write. If you're on a test and you want the carbon inside a molecule, well, carbon always has 4 sticks. Inside any molecule, it makes 4 bonds because it has 4 sticks. So if, for example, I did methane, that would be methane, right? CH4. Again, examples next page, but you're getting to see how it goes. Nitrogen, careful. Nitrogen. Ah, it's got that lone pair, right? Oxygen had 2 lone pairs, nitrogen has 1. So I'm going to have that always. So nitrogen always makes 3 sticks, 3 bonds, right? The most common ammonia, well, I said it, the most common nitrogen-containing compound is ammonia, right? Looks like that. See how the hydrogens are kind of decorative? You just kind of put them around and have them hold hands. Water we saw. Okay. Chlorine, Kim's back. Okay. Kim Kardashian, we should start calling her, you know, First Lady, right? As I record this, Kanye West has just announced that he's going to run for president, so, you know, Kim's going to be our First Lady. All right. That's the world we live in. There we go. How many bonds does chlorine make? 1. Maybe you've seen HCl. All right. Finally, hydrogen makes 1 bond. If I stick it to itself, there we go. Now, hydrogen, of course, row 1 only needs 2 to fill its outside layer, so there's no extra electrons around the outside of hydrogen. But chlorine row 2, it needs 8 around the outside, so it's got 2 in the bond. Remember, each stick is a shared pair, so 2, 4, 6, 8. There you go. So if you want a really, really quick down and dirty Lewis structure, what you got to do is make sure the rules of valency are obeyed. In other words, make sure the atom in the molecule looks like it's easy. So when it's in the molecule, carbon has 4 sticks. When it's in the molecule, nitrogen has 3 sticks in the lone pair. When it's in the molecule, we did water already. So oxygen, let me just move this around so it makes sense, right? So oxygen has 2 sticks and 2 lone pairs. That's its EZ, right? It must look like that in any molecule. Look up there, we got one. If I go like this, nice way to think about it, kind of separate them out, right? Oxygen, 2 sticks, 2 lone pairs, hydrogen, 1 stick. If we jump down to hydrogen, yeah, hydrogen just needs the 1 stick. Chlorine, 1 stick, 3 lone pairs. Okay, so that's the easy way to do it. That's the easy way to do it. Now, three minutes before the timer goes off, I've got time maybe to do 1 or 2 of these, right? Okay, so Lewis structures, easy way, right? Okay, how do I know where the electrons are, the valence electrons are in a molecule, right? So, key or trick. Each atom in the molecule must have as many bonds, i.e. its valency. Let me rephrase that. Each atom must have as many bonds as its valency is. So carbon has a valency of 4 unpaired electrons, therefore 4 sticks, right? So that's basically what I was saying on the previous page. Every atom in a compound, or in a, whatever it is, an element or a compound, in a molecule must have the same number of sticks it has in its EZ. That's what that says here. We'll see how that plays out with double and triple bonds. People get scared of double and triple bonds. It's just a consequence of less neighbors than sticks. It's actually very easy. Okay, and then sometimes we're asked how many valence electrons total. We can just count them. Okay, so there's ammonia. We did it on the previous page. I'll do it on the side real quick, right? So what you do, ammonia, I know I'm going to combine, because I got the formula. I have the formula, right? You'll always have the formula. So I got nitrogen and hydrogen. When I look at my EZ list, okay, nitrogen's got 3 sticks and a lone pair. Hydrogen just has the 1 stick, right? So nitrogen's going to go in the middle. Nitrogen's going to be the Julie Andrews, right? So you stick the one with the most sticks in the middle. Kind of think about it like the hub of a wheel, and the sticks are like, spokes from that wheel, right? And the other atoms are kind of on the rim. So we're always going to use like a cartwheel model, right? So the one in the middle has the most sticks. We surround it with other atoms, and those sticks are like spokes going out to other atoms, right? So nitrogen in the middle. Just draw it, right? And then I need 3 hydrogens. Well, obviously hydrogens. 2 sticks, if you like, become 1 stick. I'm having them hold hands. Having them hold hands. There we go. That's a single stick. All right. And there it is. Now, is it right? Well, yeah, because nitrogen looks like it's easy. 3 sticks in a lone pair. Each hydrogen looks like it's easy. A single stick. So you look at them independently. Do they look like they're easy? If yes, the rules of valency, the rules of the correct number of bonds have been obeyed. Okay. Could I do this? You think, oh, NH3, right? That equals N with an H with an H with an H. Can that work? Well, no, because remember, a bond is holding hands, right? So it's got, that'd be a lone pair, right? Maybe, right? So that would have 2 bonds not going anywhere. That's no good. Hydrogen here has 2 bonds. It makes 1. That's no good. No good. That's the only one that works. So there's only one kind of geographical arrangement that works, right? And it always is the same. The thing with the most sticks in the middle, surround it by other atoms, right? Okay. Now, I've literally got 20 seconds left. Try water, right? It's on the previous page. Don't peek. Julie in the middle. Boom. Boom. 2 sticks, 2 lone pairs, 1 stick, 1 stick. All right. Okay. Now, I just got time to tell you one more thing, okay? Sometimes they want you to tell the number of electrons, valence electrons in the structure. Remember this simple fact. A stick is a shared pair, right? And a lone pair is an owned pair. So 2, 4, 6, 8. 8 valence electrons. Oftentimes it's a multiple of 8 because octets, right? Here, 2, 4, 6, 8. 8 electrons. All right, I'm going to pause. You try the others, I'll come right back. All right, so hopefully you're okay with the concept, okay? I've given you my secret, right? So this is how I got through undergraduate organic chemistry, just with this kind of easy kind of way to kind of combine Lewis symbols to make molecules, Lewis structures, all right? And for the simpler examples, it works every time, okay? So hopefully you're able to do these, okay? If you've given it a shot, great, right? We'll see some weird stuff happen down here with oxygen and nitrogen, but hey, hopefully you're able to follow the simple idea and it'll work, right? So let's do the Lewis structure and also the number of valence electrons for all these, right? So methane, CH4, well, carbon has the most sticks, goes in the center. Hydrogen around the outside. Are the rules of valency obeyed? CH4, well, the formula's right. 1 stick, 1 stick, 1 stick, 1 stick for hydrogen, 4 sticks for carbon. Yes, rules of valency are obeyed. 2 electrons per stick, 2, 4, 6, 8. 8 electrons, that's correct. It's that easy, it's that easy. Now next one, phosphorus trichloride. Be careful, Kim's involved, right? Lots of bling little action. So, now when we think about the Lewis, right, so phosphorus is going to have, it's column 5, same as nitrogen, it's going to look like that, right? And chlorine, column 7, make that a bond. It's going to look like that, right? So remember, chlorine brings all those extra outside electrons with it, right, even though they didn't do anything. So be careful, right? Now, which has the most sticks? Not the most electrons, the most sticks. Well, it's phosphorus. Phosphorus is going to be center, and you know, that's like the hub of the wheel with the most spokes. Then I just surround it with the other atoms and have them hold hands. Have them hold hands. So 2 sticks, if you like, become 1 stick. They're holding hands. There we go. That's phosphorus trichloride. Very good, right? Is it correct? Well, look, there's phosphorus. It's got 3 sticks and a lone pair. That's what it should look like. That's its easy. Chlorine, each of them is the same. 1 stick and 3 lone pairs. Fantastic. Now, here's the thing, right? Here's the thing. So, you have to count the electrons sometimes. How many electrons are in there? Well, it's got busy all of a sudden because it's got chlorine, right? So chlorine brings all those extra electrons with it, okay? So you could kind of count around the structure and try and count all these electrons. But there's a good chance you'll get it wrong because it's just busy, right? And I'll tell you a little story. So this kind of reminds me of going to a party in college, right? Yeah, here's a guy who used to go to colleges, parties rather in college, right? And when you're a poor student and you turn up with your 6-pack of beer, right, the last place you're going to put it is in the fridge because some other student will drink your beer and you just spent all that money and you don't have much money because you're a student, right? So what do? Well, you hide your beer, right? Okay, you put it under the coats in the bedroom, you can put it under a chair, so you're hiding your beer from other people and then, you know, you can drink your beer, right? Okay, I used to hide my beer in the dishwasher. That's a trick, okay. Now, why am I telling you this? Because if you're at a party and as a student and you're trying to count how many beers there are, it's kind of hard to count them because you've got to look under the sofa and you've got to look under the coats and you've got to look in the dishwasher, right? It's kind of like here. So looking around the room trying to find electrons is kind of hard, right? Because they're kind of everywhere, okay? So there's a better way to do it. Say you're the host of the party, right? And as people come in, you just say, hey, how many beers you got? And then you just keep a tally in your head. That's the way we're doing here. Because if you think about it, the number of valence electrons an atom has is the same as its column number. So phosphorus in column 5 has 5 electrons. So hey, phosphorus, how many beers you got? Oh, 5. Column 5, right? Chlorine. Chlorine's the life and soul of the party, right? Chlorine, how many beers you got? 7, because I'm column 7, right? So phosphorus brings 5, 7, 7, and 7. So 3 7s are 21, plus 5 is 26 electrons. Easy as that, right? I kind of count them as they come through the door, right? We can kind of look around the structure and see if it confirms 26, right? So let's do phosphorus first. 2, 4, 6, 8, right? And then 10, 12, 14, 16, 18, 20, 22, 24, 26. Yeah, so you can count it around and get the same number, but there's more chance of an error. Remember, the total number of valence electrons is the sum of the valence electrons the atoms bring. They bring the same as their column number. Okay, 5 plus 7 plus 7 plus 7. All right, now, next one. Oxygen. Right, oxygen is a weird one because it's the first time we see a multiple bond, which is a double bond. And if you remember when we showed you that combustion of methane a little while ago in the thermochemistry packet, and I said, hey, I'll show you the double bond later. Here it is, right? So it turns out that oxygen, if we do our EZs on the side real quick, oxygen has 2 sticks and 2 lone pairs. 2 sticks and 2 lone pairs, right? But here's the thing, and this is the consequence of multiple bonds, right? It's O2, right? So one oxygen sticks to another oxygen. It's just got one neighbor to bond to. But guess what? It's got 2 arms, right? It bonds twice. Ah, now this reminds me of something, right? Now, when I was in kindergarten, you remember being in kindergarten, you had that one teacher that teaches you everything. Teaches you English, geography, math, science, and even PE, physical education, right? And my kindergarten teacher was this really scary woman called Mrs. White. And Mrs. White was Scottish. And the Scottish are as close as you can get to being a Klingon, basically. You've seen Braveheart, right? Okay. And so she was really, really scary, right? And her idea of physical education was this. This, ladies and gentlemen, is Scottish country dancing, okay? Where you're a bit like an oxygen, right? You stick out both your arms, and then your partner sticks out both of their arms, and you grab hold of each other twice, right? And that's called a double bond, right? So if I do that here, I turn these into bonds, right? So in the book, you'll see that. All right. Double bonding is just a consequence of less partners than sticks, right? So I'm oxygen, I've got 2 sticks and 1 partner. They go to the same place. Now if I look at them, right? 2 sticks, 2 lone pairs. Yes, it's following its EZ, right? Oxygen has 2 sticks and 2 lone pairs. So multiple bonds, doubles and triples, are just a consequence of less partners than sticks, and the same rules apply. Now this is very traumatic because back in the day, okay, this is me and this is my dance partner, Nicola Guy, and when you're 7 years old, girls are these big scary things if you're a boy, right? So there's me, and here's Nicola Guy, right? He's got his big teeth. Scary, right? And so she grabs me, and she probably outweighs me by 30 pounds, right? And she's literally throwing me around like an Olympic hammer. That's why it's traumatic. Okay, I tried to look her up. I couldn't find her on Facebook. I think she might be in prison. That's a joke. All right. Now nitrogen, try nitrogen. It's the same kind of thing, but nitrogen, you have 3 sticks and 1 partner. So guess what's going to happen? Okay, nitrogen, 1, 2, 3, same part. 1 partner, okay. And you know, this is we kind of write it like that symmetrically, and you'll see why in the next packet, okay. Oh, count the electrons. Nitrogen, column 5, 5 on the outside, 2 5s are 10. 10 electrons, we can count them. 2, 4, 6, 8, 10. Oxygen, O2, 2, 4, 6, 8, 10, 12. Column 6, 2 6s are 12. All right. Last but not least, hydrogen fluoride, H2S, okay. So hydrogen, fluorine. Well, this one, it's kind of a tie. They both have 1 stick, so put them side by side, and then just do the business. There it is. Hydrogen only has the 1 stick, that's it. So that's HF, 2, 4, 6, 8 electrons. H2S should be easy because sulfur's under oxygen, right? So it has the same Lewis. Have it hold hands. It's another governess. Right. Okay. 2, 4, 6, 8. 8 electrons. All right. Nice. Okay, now what I'm going to do, I'm going to kind of draw this to a conclusion and call it part 1. Okay? Because in part 2, sometimes, you know, here's a concept for you, right? And actually I'm going to kind of have you try this before trying part 2, right? So try if you can to do a Lewis structure for CO2, right? That's kind of right on the border between MacGyverable, you know, with the easy Lewis, and then using what we call the formal rules, right? Some teachers just teach you the rules off the bat, which work, but they're empirical. They kind of, you know, makes no sense at times, but it works. We'll show you the empirical rules. The good thing about the rules is they work for everything, but takes longer, right? If you can MacGyver it with the easy structures, do it. If you need to use the rules because it's a little bit beyond MacGyvering, yeah, use them, okay? And CO2 sits right on the border. If you can do CO2, fantastic, give it a shot, right? If it's troublesome, then I'll show you the rules on the next part 2, right? If you get CO2 and you really want to impress me, do CO3 2 minus. That is almost impossible to do by MacGyvering, right? Because it's a -2 ion. Where do those extra electrons go? There's no real way to kind of account for them. So that's why we have to follow the rules for more complex examples, right? So for more complex examples, the rules which I'll show you in part 2 always work, right? Okay. You can even, for water, do the rules. It works fine, right? You can do any molecule with the rules. That's why sometimes that's the only thing taught. However, you don't need that level of sophistication for easy ones, okay? So give that a shot. Come on back for part 2 and we'll solve those two. Okay, see you next time.